Today we're solving the Dirichlet integral, the integral from 0 to infinity of sine x over x. It keeps oscillating forever, so instead of trying to force it directly, we will calm it down with a parameter, solve that easier family, and then come back to the original integral. Here is the calmer family. We multiply by e to the negative ax inside the integrand, with a being positive. That damping factor makes the integral much easier to handle, believe it or not. Notice that when a goes to 0, the dampening disappears and we recover the original integral. At this point, we need a new technique. It's called the Leibniz rule for differentiation under the integral sign. We're going to derive the fixed limit version of it right here, and after this video we can reuse it without rederiving it every single time. Start with the ordinary definition of a derivative. The limits a and b are fixed, so the only thing changing is the t inside the integrand. Now replace each f term with the integral it represents. The bounds stay the same. The only difference is that the first integrand has t plus h and the second one has t. Since the two integrals have the same bounds, combine them into one integral. This is just linearity of integrals. Now put the division by h inside the integral. We can do that because h is not the integration variable. Now, technically, passing the limit through the integral needs justification. The standard justification is the dominated convergence theorem. We are naming that fact here, then continuing with the Leibniz rule. Once the limit is inside, the fraction is exactly the derivative of g with respect to t. Now apply that rule to the function we actually made. The only part that depends on a is the exponential damping factor. So that is the piece the derivative acts on. Inside the integral, sine x over x stays the same. The derivative of e to the negative ax is negative x times e to the negative ax. Now the x from the derivative cancels the x in the denominator. That leaves us with a cleaner integral. Negative the integral of e to the negative ax times sine x. For this remaining integral, we will use the di method for integration by parts. D means keep differentiating the sine column. I means keep integrating the exponential column. The signs alternate down the left side. The full di explanation will be linked in the description. Now read the table diagonally. The blue and green diagonals give the product terms, and the red multiplied by the last green gives back the same sine integral we started with, and that's the part that will let the equation solve itself. The same integral appears again on the right side. Move that repeated integral to the left side so the matching pieces are together. Now the left side has the same integral in both terms. Factor it out. The only thing left in front is 1 plus 1 over a squared. Now evaluate the bracket carefully. At infinity, the exponential goes to 0 because a is positive, so both bracket terms go to 0. At x equals 0, sine is 0 and cosine is 1. The bracket means upper value minus lower value, so we get 1 over a squared. Now put the bracket value back into the equation. The only unknown left is the damped sine integral, so divide by the coefficient in front of it. The nested fraction cleans up to 1 over a squared plus 1. We already solved the repeated sine integral. Put that result into f prime, and now the derivative of the whole family is just a simple fraction. Once f prime is known, recover f by integrating with respect to a. This is the standard arctangent antiderivative. Now use the two versions of f together. From the integral version, f of a goes to 0 as a goes to infinity. From the formula version, the same limit is negative arctangent of infinity plus c. That determines c, which is pi over 2. Now plug the constant back in. We just found that f of a equals negative arctangent a plus pi over 2. So the whole family is now known explicitly in terms of a. Finally, set a equal to 0. In the integral version, the dampening factor becomes 1, so f of 0 is the original Dirichlet integral. In the formula version, arctangent of 0 is 0, so the value is pi over 2. So in this video, we have derived a reusable rule called the Leibniz rule for differentiation under the integral sign. And later videos will be using this without deriving it again. And another useful result we got from this video is the damped sine formula. Our original Dirichlet integral comes from letting a equal 1 and letting b approach 0 from the positive side. But we can plug in any numbers we want. So this is a perfectly good reusable formula. Anyway, guys, that is it. I hope you enjoyed this viral integral, and we will see you next time.